Okay, we want to talk a little more about the isomorphism theorems for rings. We did the first, what is called the first isomorphism theorem. That's the most important one. And there are a few others. There's a second and a third, and there's something called a correspondence theorem. The second one I'll leave as an exercise, but we'll do the rest. And then the next topic will be talking about prime ideals and maximal ideals. Let me remind you what this first isomorphism theorem said in a picture. So R and S are rings, and let's say psi is a surjective ring homomorphism. Surjective, meaning onto maps, are often denoted by putting two arrows. Okay, so there is double arrow, means that psi is surjective. And you let I be the kernel of this thing. I is the kernel of psi. So this I is a ideal in R. So it's a subset of R. Let me just write that like that. Okay. On the other hand, once you have this ideal, you have R mod I, the quotient ring, which we defined in a lot of detail. So by the way, before you go through this, you want to make sure that you are completely comfortable with this quotient ring construction, the definition of R mod I. Because all these isomorphism theorems are basically results that help you deal with this quotient ring. So we first need to know what it is. Once you have this ideal I, you have this quotient ring R mod I, and you have this quotient map, the natural map called the quotient map. The map that takes an element to the corresponding coset. That's an element of R mod I, means a set of this form. Given this, the first isomorphism theorem says that there exists a unique isomorphism from R mod I to S, that's denoted by eta here, such that going down like this and then going up like that amounts to going right. That's the content of this equation on the left. That if you take any A, then go down, you get to A plus I, and then go up right, you get to eta of A plus I. Versus, you could have just gone right and you have gotten psi of A, because the right map is psi, and these things are equal. So this picture is a pictorial way of describing this equation. Okay. I'll recap, because this is absolutely fundamental. Given any surjective ring homomorphism psi from R to S, there exists a unique isomorphism eta from R mod I to S, such that going down right using the quotient homomorphism and then going up right using eta amounts to going straight right using psi. In particular, whenever you have a surjective ring homomorphism, let's get back to the left hand side, whenever you have a surjective ring homomorphism psi from a ring R to a ring S, then the domain ring modulo the kernel is isomorphic to S. The kernel, remember, is I. So R mod I is isomorphic to S. Okay. And we have used this already a few times to construct, to identify certain quotient rings. And there will be probably a few more in the exercises. But now let's talk about this thing called the correspondence theorem. It says that I be an ideal in R Ideal means two-sided ideal. And this triangle less than or equal to kind of sign means ideal, if you remember. And let pi from R to R mod I be the quotient homomorphism, the one that we just described up here, taking an element to its coset. Then there exists an inclusion, let me just write and then I'll explain, inclusion preserving bijection between two sets. And I'll write the sets just in words. On the left hand side you have the set of all ideals in R that contain your given ideal I. And on the right hand side you have set of all ideals in the quotient ring R mod I. There is a one-to-one correspondence between these two sets, and I can tell you what the one-to-one correspondence is. If you give me an ideal J in R that contains I, you just simply send it to its image under the quotient map, and that would be an ideal in R mod I. And if you give me an ideal in R mod I, then you send it back to its pre-image pi inverse k under the quotient map. So all the things in R that map into k under the map pi. And this sets up a bijection between this set and that set. And further, if you have one ideal here containing another ideal here, when you go forward, then the bigger one will be a bigger ideal. And same if you go back. That's the word inclusion preserving. That's what that word means. That bigger ideals go to bigger ideals, etc. So the containment relations are preserved. So this, one should sort of morally understand what this is saying. Maybe I'll draw a cartoon here. Here is R and here is I, let's say. And here is R mod I. And you have this natural quotient map pi. What happens is the elements in I, if you remember, we had this thing, A in I, if and only if its coset is same as I. But that is same as the 0 in this ring. So all these things in I go to the 0 here, the 0 of R mod I. So when you apply this quotient homomorphism, you kill the things that are in here. You collapse all those elements to the 0 element. So that's why this quotient in some sense is maybe simpler than R. What this correspondence theorem is saying is that if you give me an ideal that contains I, some J, then applying pi, I get an ideal on the right hand side. And if you give me a bigger ideal, I'll get a bigger ideal on the right hand side, etc. And furthermore, one could actually replace the word ideal on both sides by subring. Same statement hold. So what this is saying is that when you go from R to R mod I, you sort of forget what was happening inside I. Okay? But you retain all the information that you had in the ring above I. At least all the subring structure, all the ideal structure that was above I is preserved. That's the content of this correspondence theorem. And in this sense, this quotienting operation serves as a simplifying device. So you can take a more complicated ring and you can break its study into sort of two parts. You can study what was happening inside I, and then you can study what was happening above I by going to the quotient ring. And this makes a lot of induction arguments work and so on. So it's a rather useful thing. One immediate consequence of this that I'll give is what is called the third isomorphism theorem. And this says, say I have an ideal J and an ideal I, two ideals in a ring, and one is contained in the other. Yep. So like in my picture, I in J in R. So I have an ideal and a bigger ideal. Then, so I have J, so the image of J, which is pi J, which is same as J mod I, you can check. That's an ideal in R mod I. Is an ideal in R mod I. After all, you can think of J as a ring and I is an ideal in that ring. So J mod I makes sense. And you can check J mod I is an ideal in R mod I. It's really the image of J under the quotient map. What I want to say is that if you first kill I, so going mod I call that killing I, and then kill the image of J, that amounts to the same thing as killing J outright. So the proof is pretty straightforward using the correspondence theorem and the first isomorphism theorem, but I want you to sort of realize what this is saying. This is saying things like Z mod 20Z. So let's see. Here is an ideal in Z. Here is another ideal in Z. Which one is bigger? Multiples of 5 contain all multiples of 20. So we have like this. So then you could take that. That's same as Z mod 5. And this you might have seen before. Z mod 20 mod Z mod 5 is isomorphic to Z mod 5. Sorry. Mod 5 Z mod 20. And this should remind you of things like 1 over 20 or 5 over 20 is 1 over 5. Okay. The way this proof would go is you want to define a homomorphism from R mod I. You don't do it directly. You first define a homomorphism from R, and then maybe we'll go through the proof a little bit in the next one.